In this video, I'm going to talk about luminosity and brightness as it applies to stars. Please read the success criteria I plan to cover in this video. So let's start by talking about the solar constant. Now, first of all, what it means is the amount of power that arrives from the sun here at the Earth. So let's just point out what we've got here. At the sun, we have a certain amount of power that's going to be radiated in all directions, in the direction of a sphere. And that's important because remember, the surface area of a sphere is 4 pi r squared. And that means the power is going to be spread over a larger and larger area. That's intensity we're talking about, the amount of power per meters squared. I've got a diagram here. Notice this is saying if I'm at 1 radius from the sun and I have an intensity of 1, if I get to 2r, that means my intensity actually goes down to a factor of I over 4. It's an inverse square law. That means that the intensity is going to decrease as I get farther away from the sun. So, as I said, the surface area is 4 pi r squared. That means my intensity is going to be power divided by 4 pi r squared. The average power from the sun, I've got units here of joules per second. Remember, that also could have been watts, is 3.9 times 10 to the 26 watts. And we've got our distance from the Earth being around 1.5 times 10 to the power 11 meters. If I put these values together, I'm going to get the solar constant here. This value is in our data booklet, so don't use a rounded value. Make sure you use the value that's actually shown in the data booklet. So now we know about the solar constant, let's put this in context with our stars. Luminosity is the word we give to the power of the star. That intensity, or the power per area, is what we call our brightness. Now, the luminosity of its star has a relationship with its temperature. This is the Stefan-Boltzmann's law, and I go through in detail about what this means in other videos. In this case here, I've got the brightness is going to be the luminosity of the star, remember the power, per surface area. And this d is not going to be the radius of the star, but rather the distance between the star and where we're trying to observe the brightness. We also can talk about the luminosity of the sun, and this is what we use for a short form. L with a circle and a dot inside. Or if I want to talk about the brightness of the sun, I'm going to use B again with a circle and a dot inside to signify the sun. So let's do some examples. I've got two stars A and B, and they have the same spectral type, but luminosities are different. Now, I'm not quite sure what this question was trying to imply when it said spectral type, but let's say that this implies that the temperature is about the same. What is the approximate ratio of their radii? So let me go to the equation that has luminosity in it. There must be something if they've given these two values. My luminosity is going to be sigma, this is the Boltzmann constant from that equation I said earlier, times the surface area, times the temperature to the power 4. If I want to make that specific to star A, I'm going to say LA is going to be sigma 4 pi r radius of A squared, because that's how we calculate the surface area, and temperature to the power 4. And since I'm asking for a radius of A to B, let me put the luminosity of B right down here. So 4 pi, and this will be RB squared, and the temperature to the power 4. Let's get rid of some of the things over here that we can cancel out, and the temperatures. So this is going to give me LA over LB is going to equal RA squared over RB squared. And to rearrange it into the form that it's looking for, I just need to take the square root of both sides. RA over RB will equal square root of LA over LB. I'm going to substitute in my numbers. So their approximate ratio then will be 1000, or 10 to the power 3. Let's do another example. I've got some given data here in my table. It says calculate the radius of Vega, and it gives me the luminosity of the sun. So if you take a look at this value here, this luminosity says it's in units of luminosity of the sun, which means Vega here is 50.1 times the luminosity of the sun. And I have a temperature, so let's use our equation. L is sigma area temperature to the power 4. If I rearrange that, my luminosity is going to be 50.1 times the luminosity of the sun. Bottom, I'm going to have sigma, which is 5.67 times 10 to the minus 8. That value is in our data booklet. Times 4 pi times the temperature to the power 4. And Vega, let's make sure we get the right one, 9,500 to the power 4. And if I pick up my handy-dandy calculator, I get 1.8 times 10 to the power 9 meters. I'm just going to put that up here so I can have more space for part B. In part B, it says Vega appears to be much brighter than Spica in the night sky, even though we can see here that the luminosity of Spica is much larger. Why can this be the case? Well, let's start off by writing the equation that has brightness and luminosity. Now, if Spica has a larger luminosity but a smaller brightness, the only other variable in this equation is the distance. And we can see here that the relationship between the distance and the brightness is an inverse square law. So, if Vega is brighter with a lower luminosity, it must be closer than Spica. So, I hope that helps distinguish between luminosity and brightness of a star. Please read the success criteria one more time, and I hope you can say yes to all of these things.